here, and let's think about the first order transition. The key point on this topic is that the golden rule, Fermi's golden rule. In previous lecture, then the psi interacting wave function is kind of the summation c and t and n. It is key point. But here we should determine the c and t, and that is our key problem. So what is the probability that interaction causes system to make a transition from the ground state to end state? And we should know that the probability of transition, and that is a key problem on this topic. So this transition probability, the key elements is the c and t, and from the above, and the c and t can be applied to the psi I t to the n. Then psi I means that the time evolution operator t and t0, and psi I t0. Then from the complete set for the summation to m n u I t n t0 and m psi I t0. Then here this psi I t0 is that exponential I h0 t0 over h bar psi s t0. Then it also exponential I h0 t0 over h bar psi s t0 becomes psi minus I h0 t0 over h bar psi s0 from the time evolution. So here is psi s0. So from this calculation, in the psi I t0 is identical to the psi s0, zero state. So this c and t is that summation to m n u I t and t0 to m n m psi I t0 becomes the psi s0. So here we define that transition probability is that transition probability to initial state to end state. It is the c and t square. So it is a square for all kinds of m state, n, u, I, t and t0, m psi s0. In square, it is transition probability. So the calculation of this transition probability is we should calculate like this, but here anyway, then this time evolution operator, the basic form of time evolution operator is that the exponential function here in the ui as we studied before, and then time evolution operator is that time evolved operator to the exponential minus I 1 over h bar, and the integration from t0 to t prime, and the v interacting potential t prime and dt prime. That is, it is our purpose is to calculate this transition probability. So, and but to calculate this, we should let's make an example. Example helps our understanding. So, for step functional potential. And the step functional potential is not a time-independent potential, but time-dependent. Time-dependent step function, let's define that. And the step function is that here. At first, there is no potential at the t. It is not the x but the t and the vt. And here, in previous case, there was no potential, but from t equal to 0 and finite v at r, potential applied. Suddenly appeared the potential. That is the step function of potential in time. Time dependent, and at some time, and the potential suddenly appears. That is a step function of potential. So to solve this problem, and at first we should determine that this one, and the initial state and final state, and the time evolution operator, and also and the time evolution operator, and also initial wave state and square of this wave function, it makes the c and t square. So our purpose is to calculate c and t. Then the c and t is that initial state, and evolved as the time evolution operator t and t0. Then then it is in the first order. This exponential can be expanded as a Taylor series, but just only let's calculate only the first order. And 1 minus I over h bar integration to 0 to t and dt prime vi t prime I state. Then this one is that ni and the minus I over h bar n integration from 0 to t dt prime vit is that the exponential I h0 t prime over h bar v exponential minus I h0 t prime over h bar I state. Then it is because I is the initial state and n is the final state, and so initial and final is different, so it is the 0. So minus I over h bar and n, and also here when you make n in I state, and also this Hamiltonian applying to the I state, and this Hamiltonian applied to the n state, so it becomes the energy eigenvalue. So energy eigenvalue is independent with the integration in the I state, and the integration from to 0 to t and dt prime, and the exponential I and e epsilon n minus epsilon I over h bar t prime, because here h0 becomes epsilon I and h0 becomes epsilon n. So it is that minus when we integrate this one, and the integration makes that I h bar cancel with each other, n vi over epsilon n minus epsilon I, and here exponential I. Let's denote that epsilon n minus epsilon I over h bar, it is the omega n minus omega I. Then let's define that omega ni. So I omega ni t prime, and the integration from 0 to t. So from this relation, it is n vi and h bar omega ni. It is 1 minus exponential I omega nit. So, and transition probability is that is the square 0 to n is that c and t square. So it is n vi over h bar omega ni square and 1 minus exponential I omega nit, and the complex conjugate 1 minus exponential minus I omega nit. So we should let's calculate this term. Then it is 1 minus exponential I zeta and 1 minus exponential minus I zeta. Then it is 1 and 1, it becomes 2 minus exponential I zeta plus exponential minus I zeta. Then it makes that the 2 minus 2 cosine zeta. Then it's 2, 1 minus cosine zeta. Then it makes that the 2, 1 minus cosine 2 and zeta half. So it is 2, 1 minus cosine square half zeta minus sine square half zeta. Then it is 2, 1 minus 2 sine square half zeta. So it is 4 sine square half zeta. So, and this transition probability becomes 4 n vi over h bar omega ni square sine square omega nit over half. In explicit form is that 4 n vi and epsilon n minus epsilon I square sine square epsilon n minus epsilon I t over 2 h bar. So it is epsilon I is that initial energy state, and epsilon n is that the final state. But we should consider for the all kinds of from here. This transition probability makes that with time, not time, but let's make an for epsilon with epsilon n. This P and T makes that oscillation, for example, like this. Like this oscillation. Then the absolute it is decreases. Decreases like this. Okay. So here, when we think that for all of the n state, 0 to n chi, all the possible state, then it is we should integrate in both sides. So n v initial state, let's make that the 0 state square. Let's integrate from 0 minus infinity to infinity the epsilon n, and also epsilon n minus epsilon 0 half 2, and the sine epsilon n minus epsilon 0 t over 2h bar n square. And from the calculation, as for t becomes infinity, then it can be approximated by the 2 pi over h bar t. Then it makes that the 2 pi over h bar n v 0 square, and Kronecker delta epsilon n minus epsilon 0 t. So the solution is like this, and it is a transition probability for large t. So, and this transition probability means that oscillating with energy eigenvalue. Okay. So secondly, let's think that transition rate is time derivative. Definition of a transition rate is transition rate gamma I to n is that time derivative with a probability p and t. It is definition of the transition rate. Time derivative of the probability density is that transition rate. And from the above case, and for example, in this case, in above case, step function of Vt potential, then this probability to I to n is that 2 pi over h bar n v I square, and because time derivative makes that chronic delta epsilon n minus epsilon 0. So it means that if the epsilon n and epsilon 0 to 1, it is 0. Just only the ground state. Ground state is the probability is the largest at the initial state. And here for epsilon n in this case, and at finite t, like the probability oscillating like this, but the time for a long time, as a long time, and this broadness becomes sharper and sharper. So, and the most probable probability is occurred at the epsilon 0. So, and epsilon 0 is the most probable, and the very tiny, it's like this. So 0 to n probability at only focus on the epsilon 0. It means that all the possible there is no excitation. I mean that at first it is ground state, and for example, ground state first excited state and second excited state, and by applying the potential, and ground state population is the most probable, but at finite t and the excited state there may have the finite excitation, but the final after very long time, and only the ground state is most probable. The transition to the excited state and goes down to the ground state. So ground state is most probable. So here it indicates that for large t case, then we should think that the total transition rate is that total transition rate gamma is that all kinds of consider for the all kinds of quantum state to the I to n t case. Then it is 2 pi over h bar and n vi square and correct delta epsilon n minus epsilon 0. Here epsilon I. So in many quantum state, and the summation becomes integration, the epsilon n and rho epsilon n, and this summation becomes this integration. So gamma I to n t. So here, then the integration of the delta function. Makes that here 2 pi over h bar and n v I square, and delta function make integration all of the energy space is the epsilon n. Here epsilon n equal to epsilon I state. Here we call it as a rho. Epsilon n is the density of state. dn over d epsilon, we call it is the density of state. Density of state is very important in the quantum mechanics as well as solid state physics. And anyway, here the epsilon L satisfied the uncertainty principle. So, and from the uncertainty principle, energy variation and the time variation should exceed 2 pi h bar. So, and here energy variation, epsilon n minus epsilon I is the energy variation, should makes that should less than the 2 pi h over t, t case. So here we should make that transition rate. We should remember the transition rate, and the transition rate is the largest at the ground state after a very long time.